Hello and welcome to section 8.7. Today we're going to look at exponential functions. Exponential functions are used when we're trying to model naturally occurring situations, something like the growth of a colony of bacteria or the decay of something that's radioactive. These are where we're going to commonly use things like exponential functions. And actually, back in section 8.6, when we were looking at geometric sequences, we were actually using exponential functions. So today we're just going to expand on that a little bit more. As you can see from the definition here, an exponential function is in the form of y equals a times b to the power of x. Okay, now the key thing that we have to remember with this is a is going to be a non-zero constant number. B has to be a number that's greater than 0 but not equal to 1. And x is going to be a real number. So you can see down here we have a couple different cases right here. So our a value is non-zero, our b value is a number greater than 0 but not equal to 1. And we don't want it equal to 1 because 1 raised to any power is still 1. So that's why it has to be any number other than 1. Here we have a different case. Our a value is a negative value, which is possible. Our b value is a number between 0 and 1. So these are just a couple different cases that you can look at. When we go to evaluate an exponential function, what we're going to do is usually you're going to be given some values for the domain, and we're literally just going to plug those values in for our x value. So here, in the case of example 1, part A, we're given that y equals 5 to the power of x. And we're told that we need to evaluate this function for values of x that are equal to 2, 3, and 4. So if we go and we set up our table here, and I make this my x column, this my y column, I'm going to plug in the number 2, 3, and 4 in for x into my equation. So then what I'm going to do is I'm just going to solve for y from there. So for the first one, I really have y equals 5 raised to the second power, which is going to give me 25. For the next one, we have y equals 5 raised to the third power, which is 125. And for the third and final one, we have y equals 5, oops, that doesn't want to come through, raised to the fourth power, or 625. So we are just plugging in the value of x into the equation. For our next example, again, we're going to put in our x and our y into our table, and we are going to use the equation y equals 4 times 3 to the power of x. And when I plug in my x, which we're given was -2, 0, and 2. So for the first one, I have y equals 4 times 3 to the power of -2. Now remember, when I have a negative exponent, that tells me that I have to move it from either the numerator and put it in the denominator, or move it from the denominator and put it into the numerator. So this is really going to give me 4 divided by 3 squared, or 4/9. So when x is -2, y is going to give me a positive 4/9. For my value of when x is equal to 0, I have y equals 4 times 3 to the power of 0. Well, anything raised to the power of 0 is 1, so I really end up with 4 times 1, which is 4. And for my final one, I have y equals 4 times 3 to the power of 2, which really gives me 4 times 3 squared is 9. So I can see that that's going to give me a value of 36. For example 2, we have a story problem. It says, suppose 20 rabbits are taken to an island. The rabbit population then triples every half year. The function f of x equals 20 times 3 to the power of x, where x is the number of half-year periods, models this situation. how many rabbits would there be after 2 years? Notice that 20 is the number of rabbits that we're starting out with, and that is this part right here in your equation that they give you. 3 from our equation comes from the fact that we are tripling every half year. And then our x, it tells us, is the number of half-year periods. So if we want to measure how many rabbits are going to be after 1 year, that's going to mean that we have 2 half-year periods. So make sure that you pay attention to the units when you're going to write your equations or to plug values in. So in this case, it wants to know how many rabbits there would be after 2 years. Well, 2 years is really equal to 4 1/2 year periods. So when we go to plug in 2 years, we're not going to plug in 2, but we're actually going to plug in 4. So my equation then becomes f of x equals 20, which is my initial amount of rabbits, times 3, because it's tripling, raised to the power of 4, because I have 4 half-year periods. So when I simplify, this gives me 20 times 3 to the power of 4, which is 81. And again, if I multiply those two together, we can see that we have 1,620, and this would be rabbits. So in 2 years, we're going to go from 20 rabbits, assuming none of them die off in the wild, but we're going to go from 20 rabbits to 1,620 rabbits just from those original 20. For our third and final example, it says, suppose 10 animals are taken to an island, and then the population of these animals quadruples every year. Use the function f of x equals 10 times 4 to the power of x. How many animals would there be after 6 years? So because they've already given us the equation, we're going to just go ahead and use what they give us. We start out with 10 animals. We're quadrupling, which is the base of our power. And in this case, we're quadrupling every year. So because it's every year, I know that whatever I plug in for x has to be years. So the problem says, how many animals will there be after 10 years? So because I'm looking for 10 years and we know that x is in years, all I have to do is plug that 6 in for x. So I end up with f of x equals 10 times 4 raised to the power of 6. So if we simplify that, that gives me 10 times 4 to the power of 6 is actually 4,096. So if I take 4,096 and multiply it by 10, we actually get 40,960 animals will be on this island after 6 years. So this concludes part 1 of lesson 8-7. Please let me know if you guys have any questions. Otherwise, have a good day.